Hey guys, hope everybody's doing okay. What we're going to do today is continue with our periodic trends unit, and we're going to take a look at something called Coulombic attraction and see how that ties in with atomic radius. And then in future lessons, we're going to look at some other properties like electronegativity and electron affinity. The main understanding from today should come from Coulombic attraction. If you really understand that well, and if you could really understand what that trend is, you could apply that trend to everything else. All the other trends can be explained through Coulombic attraction. So there's really minimal memorization here. It's a lot of understanding one core concept and applying that and thinking a little bit and applying it to the rest of the concepts that we look at between now and the end of this unit. We're going to start out, though, by looking at trends in reactivity. This is a short little segment here of today's lesson. Let's focus on the left-hand column, lithium, sodium, potassium, rubidium, and cesium. Those are all in that group 1, and they're all alkali metals. They're very, very reactive, and I think these are super interesting and really neat because they all react very violently with water. So I have a short video clip here that I remember I watched it in high school, and I'm glad I found it, and I found it really interesting, and I think you guys will too. Pay attention to what happens to the reactivity of the elements between lithium and cesium as we move down the periodic table. And then we're going to try to explain that a little bit and look at some trends in reactivity on the other side of the periodic table. So let's take a look at that, and then we'll pick up from there.
There are 6 alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our 5th alkali metal.
Alright guys, I hope you found that somewhat entertaining there, especially at the end when that glassware breaks with the cesium piece that they dropped in. So you can clearly see as you go down a column, this matches up with your note sheet, so you should take notes as you go along here. The reactivity of metals increases as you go down a group. Now, once you understand Coulombic attraction in the next couple minutes, you will fully understand why that occurs. But a little preview of that is that elements get bigger as you move down the periodic table, right? Right here is our first row. It's our first period. Everything there has electrons in energy level number 1. That's as far out as they go. But cesium is in period 6. So there's 6 levels of electrons for cesium. So because those electrons are so far away, they react very easily. And you can see that cesium was a very vigorous reaction there at the end. So since the alkali metals are the most reactive group, which you probably knew already, as you go from left to right, the reactivity decreases. Okay, so over here in group 2, we have calcium, we have magnesium. Those are relatively reactive metals as well, but definitely not as reactive as the group 1 alkali metals. Now, on the other side of the periodic table, the trend is reversed. So as you go from left to right, the reactivity increases, and you can see that like the noble gases are blocked out here because they're not reactive at all. So we don't count them here. But we look at group 17 then, the halogens, very, very reactive nonmetals. And you recognize some of those. And then as you go from top to bottom, the reactivity decreases. So how could we remember some of this? Well, the most reactive metal is going to be francium. Now that wasn't in the video clip because it's very unstable and not a lot of it exists at a given point in time. So they didn't have enough to obviously put in a container of water to see what would happen, but it would be more violent than the cesium reaction. And then since the nonmetals increase as you go to the right and decrease top to bottom, the most reactive nonmetal is fluorine. Okay, so fluorine is super, super, super reactive for a nonmetal because it's lacking 1 electron in its outer shell. We'll talk more about that later when we do bonding. And francium is really big, right? It's in period 7, so its valence electrons are 7 levels out, so it's very easy to react. So that's our trend in reactivity. Okay, so using what we just went over in that trend with reactivity, take a look at these 4 questions on the screen. They may match up with your note sheet. And take a second, pick which element is more reactive. If you're watching this on Edpuzzle, you'll answer the questions that pop up. If you're just watching on YouTube, you can pause the video, answer them, and then see what the correct answer is. So take a second and do that, and we'll go over them. Okay, guys, very quickly, if we take a look at the answers here, we have magnesium or strontium. So magnesium and strontium are both in group 2. Strontium is further down, so reactivity of metals increases as you go from top to bottom, so strontium is the answer there. The next one is potassium or calcium. They're both in period 4, but potassium is in group 1 and calcium is in group 2. So group 1 is most reactive, so it is potassium. For number 3, chlorine or iodine. If you take a look, those are both halogens in group 17 or group 7, depending on what periodic table you look at. And the further you are to the top, the more reactive. So that means chlorine would be more reactive than iodine. And then we have silicon or sulfur. Silicon and sulfur are both in period 3. The reactivity increases left to right for nonmetals, so that means sulfur would be more reactive. Okay, guys, picking up with atomic attraction here and getting into the main part of today. The 2 questions on the screen here: what holds the Earth in its orbit, and what holds electrons in the atom? If you understand the answer to those 2 questions, then you could apply that to atomic attraction or Coulombic attraction, and this will be a little bit easier for you. So what holds the Earth in its orbit? Well, the gravitational pull from the sun obviously does, right? So there's that attraction between, if you think of gravity as that attraction between the Earth and the sun. Well, what holds the electrons in the atom? Well, the nucleus has what charge? Well, positive, right? Because there's protons and neutrons in there. Protons are positive, neutrons are neutral. The electrons are negative. So the nucleus is positive, the electrons are negative. Well, what's Coulombic attraction? Coulombic attraction is a fancy way of saying attraction of opposite charges. So something really important that you should write down, just defining what Coulombic attraction is. So that being said, we're going to take a look at trends in attraction going down a column first. That's the easiest one to look at. So in your notes, you could match all this up and draw on what you need to, but lithium has 3 electrons total, 2 in the first level and 1 in the second level. So if you drew the electron configuration, it would be 1s2, 2s1, and that makes sense. You go to sodium, it has 2 in the first level, 1s2, and then the second level is 2s2, 2p6, so you have 8 electrons in that level. And the third level is 3s1. There it is. Potassium, you have 1s2, 2s2, 2p6, so there's 8 electrons in the second level. Then you have 3s2, 3p6, that's 8 in the third level. And then you have 4s1, so there is your 4th level and your 1 electron there. So you can draw all those in, but really the main thing here is how many do you have in the outermost level? Like, we care about what our outermost level is. So maybe you got that from some of the earlier lessons as well. Those valence electrons are very, very important. And we'll talk more about those in the bonding unit. But anyway, Lithium has electrons in the furthest level out, for that being the second level. Sodium has electrons in the third level, potassium in the fourth. So let's isolate those and just take a look at what those outermost electrons are. If I were to ask you which element has a stronger hold, a stronger Coulombic attraction on its valence electron, which one would you pick? Well, if I'm looking at this, I see my electron here in lithium is 2 levels away, sodium is 3 levels away, potassium is 4 levels away. So if I'm thinking about some common sense, I'm using some common sense right now, I would say that lithium has a stronger hold on its valence electron. Well, why? Because it's closer to the nucleus. Okay, so as you go down a column, that's what happens. You get further and further away. The atoms get bigger and bigger and bigger. So the electrons in the outermost level have less of an attraction with the more levels you gain, the more levels you add going down a column. So strongest attraction you could label as lithium, and then your weakest attraction you label as potassium. So there are really 2 reasons here. Number 1 is lithium is the closest one to the nucleus, and potassium, the valence shell electron, is the farthest from the nucleus. There's something else we need to consider though, and that's shielding. So lithium has the least amount of shielding, and potassium has the most amount of shielding. So let's talk about that really quick. I have a demo here, but I'm not in class to do that, so we'll talk through it. Think of this as a magnet, okay? One magnet is lithium, your other magnet is that electron, and there's some attraction there, right? The 2 magnets want to come together. So let's say you did have 2 magnets and you pieced them together, like they were attracted to each other and they were actually connected. And you try to pull them apart. Depending on how strong the magnet is, it might be a little bit more difficult to pull those apart, right? Let's say we have a stronger magnet. Well, if you go down to potassium, let's say you have the same magnet, but you put a bunch of like index cards or a bunch of paper in between the magnets. Well, the magnets will still stick, right? The paper will be in between. The magnets will still be attracted to each other, but you could pull those apart very easily. I have a really strong horseshoe magnet at school that I do this demo with, and students have a really hard time pulling the magnets apart here when I have no shields in between. But when I put a stack of index cards in between, students separate it very easily. So I wish I could do that demo for you guys, but maybe you could kind of visualize that. So lithium has 1 shield, okay? So this acts like a barrier almost, like it minimizes some of the attraction between that valence electron and the nucleus. Look at potassium. 1, 2, 3. 3 shields for potassium. So 3 levels between the nucleus and that valence electron, shielding that from some of the attractive force. That minimizes some of that attractive force there. So in your notes, you can copy these down. 2 factors that affect how strongly an atom attracts its valence electrons. Number 1, distance from the nucleus, and number 2, shielding. Number of energy levels between the nucleus and the valence electron. So take a second and jot those down. To summarize this then, as you move down a column, the attraction what? Well, obviously the attraction decreases. Stronger attraction at the top, weaker attraction at the bottom. Now, let's talk about moving across a row. A little bit trickier here. Let's look at carbon, nitrogen, oxygen. 3 elements. All of those are in period 2. So all of these have 2 electrons in the first level. Carbon would be 1s2, and then it would be 2s2, 2p2. So that gives you 4 electrons in the second level. Nitrogen is 1s2, 2s2, 2p3. So you have 5 electrons in that level. Oxygen is 1s2, 2s2, 2p6. So you have 6 electrons in that level. So let's take a look at our rules that we just went over. We said the 2 things that make an impact on attraction. Number 1 is number of energy levels. Well, how many energy levels do all 3 of these things have? Well, they all have 2, right? So they all have the same distance between the nucleus and valence electrons. So that's a tie. It's a 3-way tie here for that. So what's the second thing we looked at? The second thing we looked at was shielding. So shielding was number of energy levels between the nucleus and the valence electrons. So if you take a look at carbon, nitrogen, and oxygen, how many shields or how many shielding levels do all 3 of those have? Well, they all have 1. Carbon has 1 shield, nitrogen has 1 shield, oxygen has 1 shield. So that's a tie. Well, if energy levels is a tie, shielding is a tie, what's our tiebreaker? Well, it can't be these things, obviously. So what's different then between carbon, nitrogen, and oxygen? Well, clearly the number of electrons is different, but they're all in the second level, right? So they're all relatively the same distance from the nucleus. So what's our tiebreaker? We have to count how many protons we have. So carbon has 6, nitrogen has 7, oxygen has 8. We get that from the atomic numbers, 6, 7, 8. So that being said, you want to think of where those protons are located, the nucleus. And then you want to think of that, those protons, that's what the nucleus charge is going to be. The nucleus for carbon is a +6, nitrogen's a +7, oxygen's a +8, because the neutrons are neutral in the nucleus. Think of this. Think of these number of protons as how strong the nucleus is pulling in on the valence electrons. So carbon is pulling on them with like a pull of 6 protons. Nitrogen's pulling with 7, oxygen's pulling with 8. So that tells us that oxygen has the strongest attraction here. Carbon has the weakest. So moving left to right across a row, across a period, the attraction, the Coulombic attraction is increasing. Why is that? It increases across a row because the stronger Coulombic attraction is determined by the number of protons. The number of protons increases from left to right. So that nuclear charge, okay, that nuclear charge, what we call the charge of that nucleus, that's getting bigger and bigger as you go from left to right across a row. All right, guys, now we're going to take a look at trends in atomic size, and we're going to try to relate that to our trend in attraction that we just talked about. Okay, so taking a look at fluorine and chlorine, first thing I would do is take a look at the periodic table and find them. So I look at the periodic table, I find fluorine, and I see fluorine is in row 2, or the second period. So that is period 2. Chlorine's right underneath it, period 3. So what does that mean? It means that fluorine has valence electrons in the second energy level. So here's our nucleus, okay? Here's our first level, okay, pretend that's a full circle. And then here's our second level. So the fluorine's valence electrons are in that second level. Whereas chlorine, you have your nucleus, you have level 1, level 2, and then level 3. So the electrons are further away in chlorine. So it's pretty easy to figure out which of these atoms is bigger because they're both in the same group. And all you have to understand here is as you go down a group, then the size is going to increase. It's easy to understand that because you know that the number of energy levels increases as you move down a group. When we did the lesson on the quantum mechanical model and we did the electron configurations, that was one of the things that we looked at was that left-hand side of the periodic table that gave us what period we were in, what energy level we were in. So the higher that number is, the more energy levels you have. So here's your overall rule right here. You could tie this into attraction because attraction decreases as you go down a group because that size increases. So we'll talk about that trend. An easy way to remember that in a little bit. I just have this image again for you so you can see that lithium, sodium, and potassium, the first example we looked at, lithium has a stronger attraction because it's a smaller atomic radius. Electrons in the second level only, so this is similar to fluorine. And then potassium has electrons in the fourth energy level. Clearly 4 levels out is bigger than having electrons only 2 levels out. So if they're in the same group, you can take a look at energy levels and figure out which one is bigger based off of that. Going across a row, going across a period is a little bit trickier. So if you take a look at these, you have carbon, nitrogen, oxygen, same example as before, but here I'm asking you which atom is bigger. So we have A, they're all the same size, and then we have obviously carbon, nitrogen, or oxygen to pick from. So take a guess and see which one you think is bigger, and then we'll go over it. Okay, so you may want to think it's A, that they're all the same size, but that is actually wrong. Yes, they all have 2 levels of electrons. That's true. But those could vary a little bit in distance between the nucleus and that outer shell. Okay, so they all have 2 energy levels, but because of the number of protons changing, that's going to change our size by a little bit. So just think about it. Carbon has 6 protons, nitrogen has 7, oxygen has 8. We did say previously that oxygen has the stronger attraction. Okay, so since oxygen attracts those electrons stronger, with a higher force, it's going to pull them in a little bit closer to the nucleus because that oxygen has 8 protons pulling them in. Carbon only has 6. So these 2 electrons in carbon are still being pulled in, but they're not being pulled in as much as we have over here. Okay, so this is my attempt at making a stronger pull of electrons there for oxygen. So what does that mean? Well, that means carbon is actually larger because these electrons are pulled in a little bit less than the ones on oxygen are. So moving across any row, the atoms get smaller because of the energy level being the same. They're all level 2, but the attraction increases due to the increasing number of protons. So you're getting smaller over here with oxygen because the attraction's increasing. It's pulling those electrons in more compared to carbon where you have less attraction, so less pull on those outer shell electrons. Now, let's take a look at an example here, real life example. This I use year after year. It really helps students understand this. We're going to bring some prom drama into this whole discussion here. Okay, so what you want to do is think of the prom, right? I've chaperoned a couple proms in my day here, so I've seen a few things. You have 2 distinct couples at the prom usually. You have, you can tell just by looking. You have that one couple that's there, right? That is totally 100% in love, right? They have like the wedding date planned, how many kids they want, like the whole thing's planned out already, right? They clearly have a very high sense of attraction to each other. Okay, we all know who I'm talking about here. What does that mean then in relation to their size on the dance floor? That's what you need to think about here, guys. So a strong attraction between this couple at the prom means what in terms of how far apart they are on the dance floor? Well, it means they're not very far apart at all, right? It's uncomfortable sometimes, right? So they're very, very close to each other, which means they take up a very small size on the dance floor, right? So same thing we just talked about. Atoms with a strong Coulombic attraction means those electrons are pulled in closer to the nucleus. So the atom is smaller, right? Takes up less space. Well, then you have another type of couple at the prom where clearly one member of that couple asked the other one to go, probably had some fantastic promposal, game plan all figured out. And the other person really didn't want to go with them, but they felt bad, right? So they're there anyway. So you can definitely say that there's a weaker attraction between those 2 members of that couple, right? The Coulombic attraction, the attraction is just not there. So when they're dancing, they're a little further apart, right, than our couple that's deeply, deeply, madly in love up here. So because this couple has a weaker attraction, they're further apart on the dance floor, so they have a larger size. This ties directly into what we're talking about the electrons. So weaker Coulombic attraction within an atom means those electrons in the outer level are not as attracted to that inner level. So they tend to stay a little bit further out, right? They're not as attracted, so they're not as close. So the atom has a larger size. I tell students all the time, do not memorize a million trends that we're going to go over. Know one of them. Know one trend really, really, really well. It's the trend in Coulombic attraction. Then use a couple of my silly examples, think a little bit, and everything else just falls into place. It's really easy. Quick visual for you. Attraction increasing left to right. Okay, so size decreases left to right. High attraction over here, less attraction over here. Going down, atomic radius is increasing. Clearly see we're getting bigger here. Energy levels increasing, attraction decreasing. Cesium, 6 levels of electrons, very weak attraction, big space that it's taking up. Hydrogen, 1 level, okay? Very close, very highly attracted, small size. Pretty easy to think about. Okay, take a second on your note sheet and circle the atom that is larger in each of these. Then we'll go over the answers and we'll do the one on the other side of the page. Okay, just to check our work here, magnesium or strontium, the one that's larger is strontium. Okay, strontium is in a bigger level, level 5 compared to level 3. Potassium or calcium, We want the bigger atom. Calcium is further to the right than potassium is. And as you go left to right, the size gets smaller. So the larger atom is K. Chlorine or iodine. Iodine is in group or period 5, and chlorine is in period 3. So iodine has 5 levels, chlorine has 3. Clearly iodine is bigger. And then silicon or sulfur. Silicon is larger because it's further to the left. Okay, take a second and do this then. Circle the atom with the stronger attraction. Give you a second to do that and we'll go over it. Okay, this is easy. It's the exact opposite of what we just did. So remember, there's an inverse relationship here. If you have a very, very strong attraction, you have a very, very small size. If you have a very, very weak attraction, you have a very, very big size or a bigger size. So the ones on the previous slide that were larger are going to have the weaker attraction. So here we want the stronger attraction. So we want the atom that was smaller, right? So it's the exact opposite of what we circled on the previous slide. Easy. Okay, I'm trying to wrap this up in the next couple of minutes here. The trends in size of ions. If you look at what we have here, we have lithium going into lithium plus 1, sodium going into sodium plus 1. We're creating an ion here. Well, when we remove an electron, okay, when you take an electron out, look what happens to the size. The size gets smaller. That makes sense, right? Because you're taking an electron away. So if you lose weight, you're going to get smaller, right? So that's the same thing here. We're losing an electron, so there's less there are less electrons then for the atom to pull in on. So it pulls in on all of those remaining electrons a little bit more. That's your explanation here for that. So because of the one less electron, or if you lose another 1, 2, or 3 less electrons, the other electrons are pulled in a little bit closer because of that, creating a smaller size. The opposite happens when you add an electron. So if you add an electron to fluorine, you go from F to F minus 1, you gain an electron, right? So now all that pull from the nucleus has to be spread out between more electrons. So because there are more electrons, here's our explanation, because there are more electrons being added and more electrons total, the attraction is more spread out to all those electrons. So the size tends to increase by a little bit. So think about it. It's easy. You add something, it gets bigger, right? You add an electron, it gets bigger. You just have to pay attention to your charge. Okay, last thing for today. If you take a look at sizes of different ions, it can get confusing. So if you look at potassium and chlorine, which one is bigger? Well, potassium is in level 4. Chlorine's in level 3. So looking at the neutral atoms here, potassium is definitely bigger because it's in level 4, whereas chlorine only gets its electrons to the 3rd level. Well, let's look at the ions though. K plus 1 and Cl minus 1. Now, look at the protons. K plus 1 has 19. Cl minus 1 has 17. We get that from the atomic number, right? But look at the number of electrons though. K normally has 19 electrons, but it's a positive 1 charge. So that means it had to lose an electron. So now how many does it have? 18. Look at chlorine. Neutral chlorine had 17 electrons, right? But it's a -1 charge, so it gained an electron. Right? A -1 charge, it's an extra negative, so you gain an electron. This is from last unit. Both have 18. So if you take a look at where they are in the periodic table, both of these have the same electron structure as argon. So you're like, okay, the number of electrons is the same. Well, how do I know which one's bigger or smaller? Well, if the number of electrons is the same, and 18 electrons would give you the electron configuration for the element number 18, which is argon. What's our tiebreaker? Well, the tiebreaker has to be the number of protons. So we have 19 protons on K plus 1, 17 on Cl minus 1. If this is a tie here, okay, 18 electrons is in energy level number 3, okay? So all of those are in period 3. So shielding is a tie, energy levels is a tie. Protons is our tiebreaker. 19 for K plus 1 means stronger attraction. So K plus 1 with a stronger attraction will be smaller, and Cl minus 1 will be larger. That's as hard as it gets today. Okay, so if you have ions, figure out your number of electrons, and then protons, find your stronger attraction, that's your smaller size. So take a second and look at these. 1, 2, and 3, and 4 are very easy. 5 and 6 are a little more complicated. For 5 and 6, you have to do what we did right here. So take a minute and do that. That'll be the last thing for today. And if you're on Edpuzzle, you'll put your answers in, and the right answer will show up so you can check your work that way. So take a second and do those, and then I'll go over what the homework is going to be. Okay, homework is pages 21 through 23. This is subject to change based on what year I'm teaching this and what numbers those are in the packet. So just pay attention to any sort of announcement in class or on the lesson planner for what you need to do there. But that takes care of a large chunk of what's left in this unit. There's only a few small periodic trends left, electronegativity and electron affinity. And we'll do those in the next couple days and wrap this up. All right, guys, that's it. Thanks.